All right. Good. So we're gonna start chapter 4 today, starting with functional limits. And as is usually the case with every chapter in our book, the chapter starts with an introduction, and that introduction has a motivation of what we're trying to accomplish here. And in this particular case, this introduction will consist of 2 or 3 specific examples that will be important. All right, let me see. Okay, so let's see if this works. Just a sec. I see who is the one that. Okay, that worked. Okay, good. So good. All right. So here's what we're gonna do. Let me share you. I hope you can see it. Okay. So this is from our book, and this first one over here will be the graph of Dirichlet function. All right. I'll write it down in just a moment. What the definition of the function is, but you should remember it because we talked about it before. So this is a function that assigns 1 to every rational number and 0 to every irrational number. All right. And what we want to talk a little bit about is the concept of continuity. I mean, you all know continuity from your calculus classes, and you know the idea, the intuitive idea is that the graph can be drawn without lifting the pencil from the paper. And if you take a look at this graph, you'll notice that, I mean, this is the best way to draw it, actually. I mean, it's not quite an accurate description, but there's a bunch of rational numbers, right? The rationals are dense. So among every 2 numbers, there's a rational number. So we're going to have a point right here on top, by 1. But also there's an irrational number because the irrational numbers are dense as well. So we'll also have a 0. So the function looks kind of like this, right? And then let me now do it this way. So this is a function we're talking about. Let's call it the function g. So this will be Dirichlet's function. And it's defined as g of x equals 1 if x is a rational number, 0 else. And then our question right now is if this function could be continuous, right? At any point, at any particular point, right? And for example, let's say, is it continuous at 1/2? And here's the thing though. For this function to be continuous at 1/2, it would mean that if we get a sequence of numbers that get close to 1/2, the function should be getting close to g of 1/2, right? That's the definition of continuous, the intuitive way. I mean, I haven't defined it properly yet, but you know the definition already. So this would mean that if xn is a sequence, if xn is a sequence that approaches 1/2, then is it true that g of xn approaches g of 1/2? That's the question, right? Now, what is g of 1/2? By the way, if you can also use the chat feature. If whenever I ask, you know, little things like that, you want to answer with the chat, I take a look at it in real time, so that's perfectly fine. So in this case, g of 1/2 is 1, right? It's a rational number, so g of 1/2 is 1. And then here's the thing, though. We can get a sequence of rational numbers that get close to 1/2, right? So if Rn is rational and Rn approaches 1/2, then what is G of Rn? Well, they're all rational, so G of Rn is 1. And in this case, yes, right? Because these numbers they're all 1 and they're approaching 1. Perfect. So in this case, the limit of G of Rn when n goes to infinity is 1, which matches G of 1/2. So we're happy. It seems like it could be continuous at 1/2. However, many of you are already thinking, what if instead of using a rational number, we use irrational numbers? We can also take a sequence of irrational numbers that approaches 1/2, right? So, however, if In are irrational, then G of In is 0. And then the limit of G of In will be 0, which is definitely not the same as G of 1/2, right? So we cannot have a continuous function having two different limits like this. So what's happening here is that this function G, this Dirichlet function, is actually not continuous at 1/2. And it's not hard to see that this little exercise that we just did here would work the same if instead of using 1/2, we use any other number, right? So Dirichlet function is an example. So this is a function, and G is a function. G is a function which is discontinuous everywhere, right? So at no point does it satisfy to be continuous. So it's an interesting function. You should remember it for these properties. Now, we're going to modify it a little bit to create a new function. So this is a modification of Dirichlet's function. So new function. And this one will be like this. Observe. So now we're going to make it x if x is rational and 0 else. A little bit different, right? How would the picture for this one look like? Let's see if we can draw it over here. So it's going to be x, where x is rational. So that's like the line y equals x, but only for the rational numbers. So it has a bunch of holes, right? So it looks like these little dots that we were talking about, right? Kind of like this. So for every rational number that you can pick here, for example, if I pick 1, well, I have a dot right here at height 1. If I pick 1/3, the same thing, because that's a rational number, and so on. So every rational number will have a little dot right here on this diagonal. But every irrational number will be 0, so it looks like this. And again, I mean, these dots are not the best possible representation, but it's the best thing that we can do. Let me show you on the book how it looks like. So in the book looks like this, right? Which is more or less the same type of picture that I was showing you a moment ago. So it kind of looks like this. And now the question is, let's talk a little bit about the continuity at 1, at 0, I mean. So is H continuous at 0? Right? Now, observe what's going to happen here. See, we can pick a sequence of rational numbers or a sequence of irrational numbers. If we pick irrational numbers that are getting close to 0, so if we pick in approaching 0, where in is not rational, then we know that h of in is 0 for all of them, and so the limit works, right? The limit is 0. But what if we have a few rational numbers among them, or if the sequence is all rational numbers? So if we pick rational numbers approaching 0, well, then h of Rn will be Rn, right? But what is the limit of h of Rn? Well, that's the same as the limit of Rn. And we said that that sequence was approaching 0, right? So this limit will be 0 as well. So for this particular one, even though it's also messy like Dirichlet's function, now we made it so that it is continuous right here. Right here, it's continuous. Nowhere else, right? If you pick any other point, we can do the same as we did for Dirichlet's function. We can create a sequence of irrational numbers where they're all 0, or we can get a sequence of irrational numbers where they're all equal to whatever this other number is, right? So for any other number, it will fail, but for 0, it works. So this h is an example of a function that is continuous at only one point. H is continuous at 0 and nowhere else. All right. Questions so far? All right. So we have yet another example of an important function here. And this one is a bit more complicated. So let's define it first, and then I'll tell you what. It also has a name. So this is Thomae's function. And it's defined as follows. So if you want to know what t of x is, it is the following. It is 1 if x is 0. It is 1 over n if x is a rational number of the form m over n, a rational number that is not 0, and this is already in lowest terms with positive denominator. And otherwise is 0 if we don't have a rational number. All right, so let's try to understand this function first a little bit before we try to draw it or do the graph of it. All right, so what does this function look like? So what is, for example, t of the number 3? Well, 3, we can write it as 3 over 1, right? So we're in this second situation, right? We could write the x as something over something, and the denominator is 1, so this will be 1 over 1. So t of 3 is 1, right? And the same is going to happen for any integer, correct? So if we do t of -2, well, that's t of -2 over 1. So the same thing happens. The answer is 1, right? Now pick a rational number, your favorite rational number. I'm going to pick a positive one. How about 22/7? Well, if I pick 22/7, then I look over here and it's 1. This is already simplified, right? I cannot cancel anything else. So 22/7 tells me that this is going to be 1/7. Correct? And if you pick anything that is not rational, like say square root of 2 or pi, well, you get 0. Okay? All right, so now let's attempt to do the to graph this function a little bit. How does it look like? Let's see. So if we pick 0, we got 1, right? And we said that the same happens with 1 and with 2 and with -1 and so on, right? So those values are 1. Now if you pick 1/2, well, that's going to be 1/2. And if you pick 3/2, that's going to be 1/2. If you pick -1/2, that's going to be 1/2, and so on, right? So all the ones that are an integer over 2, like an odd integer, like 5/2, 7/2, all of them are going to be 1/2. Then we can think about something like 1/3. And 1/3 will be 1/3. But 2/3 will also be 1/3. And then 4/3 will be 1/3, and so on, right? So these little points distance, this is too close to be 4/3. Let's fix it a little bit. 4/3 should be more over here, and there's another one over here for 5/3, and so on. Then we have the 1/4, the 1/5, right? So 1/4 will be right here, and we also have 3/4 right over here. And then the entire thing repeats itself, right? It's sort of periodic. So here's the picture from the book. Let me show you. All right. It looks like this, just like we were saying, right? So we have these numbers over here that are 1 at the integers, then 1/2, and then we have this one. So for every rational number, you only go as high as its denominator. And then we have all of these points that are zeros for the irrational numbers, right? This is like the best description we can create of this Thomae function. It looks like a bunch of little trees, right? And little trees and these like lamps on top, if you want a bit of a description like that. All right? So that's how it looks like. And then we're gonna at the same way talk about the continuity here. All right? So let's pick a rational number first, right? So if you pick a rational number, so we have the same question as before. Is this continuous? Is this function continuous for some values? All right, and for example, let's start by picking a rational number. So if we pick a rational number, then here's the thing. We can find a sequence of rational numbers that converges to it, and also a sequence of irrational numbers, right? But in here, let's just use irrational numbers. There is a sequence of irrational numbers, In, such that In converges to C. We know that happens, but then what is the Thomae function of In? Well, it's an irrational number, so it's 0. It's the ones that stay right here in the bottom, right? That I stopped drawing my own picture because I showed you the other one. But we have all of these dots for the irrational numbers right here. So these are all zeros, right? But what is TOC? Well, T of C is going to be, it's a rational number, so it's going to be 1 over n for some n, right? So definitely it's not going to be 0. So T of C is not equal to the limit of the TINs. So it's not continuous at the rational numbers. So T is not continuous at C if C is a rational number. All right? Now, what about an irrational number? What would happen with irrational numbers? Well, so I'm not gonna provide you all the details. I'm just gonna give you an idea of what would happen if we pick irrational numbers by showing you a specific one, right? So let's pick square root of 2 or pi. So consider square root of 2. All right. So for square root of 2, if I get close to square root of 2 with irrational numbers, so if in approaches the square root of 2 and in is an irrational number, then I'm happy because h of in is going to be 0. So the limit of the hins will be 0, and 0 is the same as h of square root of 2. So if we do it that way, I'm happy. The problem, as you are thinking, is, well, Professor, what if we use rational numbers? Right? What if we use rational numbers? Well, let's see. If we use rational numbers, right? So what is the square root of 2 first, right? What is this number square root of 2? As an approximation, well, it's like 1.4, right? So square root of 2 is about 1.4142135770, etc., right? More or less. So one way we can approximate square root of 2 with rational numbers is if we go by their decimal approximations, right? For example, we could, here's a sequence of rational numbers. So sequence of rational numbers that get close to square root of 2. Here's one. First, go 1.4, right? What's 1.4? Well, that's 14 over 10, or 7/5. Then go 1.41, right? And that's, what's that? That's 141 over 100. And I think that's already simplified. Then go 1.414. And that's 1414 over 1000, right? And then 1.4141, which is the same as 14141 over 10,000, etc. You see what I'm doing here, right? Okay. Now, what happens when I apply the t function? So what is t of this number? So that we can see what's the t function doing to this. Well, remember, what it's doing is it's taking the denominator, right? The 1 over the denominator. So this will be 1/5. This will be 1 over 100. This, I haven't simplified it. I can take a 2 out of it, and I think then it will be fine. So I think this is 1 over 500, and this is 1 over 10,000, and so on. Now, what I want you to realize, though, is that these numbers are becoming smaller, right? So if you use a better approximation to square root of 2, if you get closer and closer to square root of 2, you're going to need more and more digits, right? And by using more and more digits, the denominator will be bigger and bigger. Even if you simplify it a little bit like this is 500, it's not 1,000. even if you simplify it a little bit, it will still be very, very big, the denominator. So the point that I'm trying to make is that these numbers are approaching 0. They're becoming smaller and smaller. So the details are actually in one of your exercises, maybe not in this section, but in a later one. So it turns out that the limit of these rational numbers is 0. And 0 happens to be h of square root of 2. So look at what's happening here. For irrational numbers, it doesn't matter if we pick a sequence of rational numbers or irrational numbers. If you pick irrational numbers, then they're all 0. If you pick rational numbers, then they're not 0, but their denominators become bigger and bigger and bigger, so the numbers become tinier and tinier and tinier, and therefore we still approach 0. So what's happening here is that this function, believe it or not, is continuous. This is continuous at square root of 2. Now, there wasn't anything special about square root of 2. I could have picked pi or square root of 3 or any other irrational number that you like, e, and I could have done exactly the same thing. So this function, this Thomae function, I wrote h here, but it should be t. This Thomae function is actually continuous at every irrational number, and discontinuous at every rational number. Look at that. So the Thomae function is continuous at every irrational number, but discontinuous at every rational number. Look at that. That's an incredible property, right? I mean, if somebody asked you, come up with a function like that, you would be like, wow, I think that's impossible, but in fact, it is not impossible. All right, so these are the 3 functions that, like I said, are section 4.1. They're meant as a way to motivate you, right? To show you that continuity, when you talk about continuity of functions, is actually an interesting thing. And that there are different things that can happen here. For example, you can ask if it's possible to do it the other way around. Can we get a function that is continuous at the rational numbers, but discontinuous at the irrational numbers? So switch irrational and rational here. And a spoiler alert, that one is not possible. So it will be something that we'll learn about some of the conclusions of the theorems coming ahead. All right, so let's move along to the next section. So now we'll start 4.2, and these are functional limits. All right, and we'll start with the definition. So definition 4.2.1, and here it is. So this is something that you're familiar with. I'm just gonna try to phrase it in a slightly different way. So here we go. We say that we have a function from a to the real numbers, and we pick a point in the domain, a limit point. So I can tell you right away that limits don't make sense with isolated points, right? If we have a point in a domain that is isolated, you cannot get close to it, So limits don't make sense for isolated points. So only for limit points. We say that the limit of a function f when x approaches c is L if, and here we go, this is the definition you all probably know, for every epsilon greater than 0, there exists delta greater than 0, such that whenever 0 less than x minus c less than delta, it follows that f of x minus L is less than epsilon. All right. Now, the way you should read this definition is as following, is the following way. This is telling you that you can get f of x as close as you want to L. So this epsilon tells you how close you wanted it to be. So for every epsilon, no matter how close you want it, I can find a delta such that if the values of x are closer than delta to c, then the values of f of x will be closer than epsilon to L. That's the way we should understand it. And there's a better way to explain this definition if we use neighborhoods. So how do we write this definition with neighborhood? So here it goes, an equivalent definition. So equivalently, all right, so here's an equivalent version. So for every epsilon, there is a delta such that and then let's see, we're saying if this happens, then this happens, right? And I'm just gonna try to rewrite what is the meaning of this. And remember, the idea is to remember that the absolute value of the difference of two numbers is like the distance. So this is a way of saying that the distance from x to c is less than delta, right? So that means this number x belongs to the delta neighborhood around c. So if x belongs to the delta neighborhood around c, and x is not equal to c, right? That's this greater than over here. This greater than 0 over here prevents x to be equal to c. That's the only thing it does. So if this happens, then f of x belongs to the epsilon neighborhood around L, right? So if you can see, this is a more natural way of looking at the concept of continuity of a function. It's telling you that if you have numbers in the delta neighborhood, they go inside the epsilon neighborhood, right? That also, we can make a little picture about this. So let's try to make a picture about what's happening here. The picture will be like this. So we have some function, and this is the c that we're choosing. And then what we're saying is you can pick, if we want the limit to be L, you can pick an epsilon neighborhood. So you can make this epsilon. And then you should be able to find some delta neighborhood over here, delta neighborhood around C, such that when you map these up, these numbers all fall inside your original one. So this part over here, when you map this segment over here, this neighborhood, it goes inside. It goes like this, inside this part over here. All right? So in an even shorter way, so we're gonna take this one step further and So this is also another equivalently. So equivalently, we can use the image notation, and we can say that f of the delta neighborhood around C, take away the center, goes inside the epsilon neighborhood around L. So for every epsilon greater than 0, there is delta greater than 0 such that this happens, right? If you take a look at it, it says exactly the same. It's saying that when you apply the function to this little neighborhood, so when you apply the function to these numbers over here, they all go inside this epsilon neighborhood around L. That's what it's saying. All right? Okay. Questions so far? I saw, by the way, some questions that you guys did in the chat that either you figured out on your own or someone else answered. Thank you for that. I didn't take a look at them at the right moment.
Professor, I have
Yes.
a question on the drawing. What is the line? What does the line represent? The one that goes through, like the intersection of the neighborhood around C and the neighborhood around L.
The line, you mean this blue thing is supposed to be the curve. So this is supposed to be the graph, so like the function.
Mm-hmm.
And which line you're talking about?
Oh, it was that line.
That one, yeah. So this is like supposed to be the graph of the function, right? In case there's, I think there's a better, let me see. I think there may be a better graph in the book. Let me find it. I think there is one. Yeah, like this. This is probably a better one. So you can see, so this is the graph of a function. And you start for the limit to be L, you need to show that no matter what little neighborhood you pick around L, right? This is V epsilon of L. Mm-hmm. You can find a delta neighborhood around C. So here's C, and you can go around C so that when you go up to the function, those numbers fit inside the epsilon neighborhood you had picked before. Okay. All right. That makes sense?
Yeah.
Great. Any more questions? Okay, so I wanted to do an example now of how we actually do this. I mean, some of you have a bit of practice, and in fact, after that example, we're gonna see a little theorem that is gonna help us, because if you think about it, what we have worked with are not limits of functions, but we've done a considerable amount of work with limits of sequences, right? We had an entire chapter where we studied limits of sequences. So the first thing we want to do is relate limits of functions, which is what we just learned right now, the definition that I wrote down, with limits of sequences. And if we put them together, then you will be able to use all the nice theorems and results we already know for limits of sequences. So that's going to be our goal. But first, let me show you an example. So this example is, let's say, it's example 4.2.2. And we want to do, we want to find out, so prove that the limit when x approaches 2 of x squared is 4. So a very simple limit. I mean, we know already that this is the case. We know that x squared is a continuous function. We learned that in calculus. And so then this is one of those we can do by simply plugging the number. But based in our new definition and this very precise definition of what the limit means, let's see if we can figure it out. What is it that we need to do to show this? We need to show that need to show that for every epsilon, there is delta such that x squared minus 4 is less than epsilon whenever 0 less than x minus 2 is less than delta, right? That's what we need to do. And generally, these proofs go as follows. So you pick an arbitrary epsilon, and you need to find out the delta. You need to say delta equals this. And delta usually depends on epsilon, right? Because makes sense, right? The smaller the epsilon is, maybe the smaller that the delta we're going to need to use is going to be as well. So let's do a little bit of the discovery first. So how do we do this? Well, you start with what you want, right? So we want x squared minus 4 less than epsilon. And we then factor this, right? So what is this? This is x minus 2 times x plus 2 less than epsilon, right? Now, we're sort of in great shape now because this we can manage, right? This x minus 2 is the part that we can make less than delta. So this we can manage. The problem is this x plus 2, right? So here you would like to do something like this. You would like to write this is the same as this, right? And maybe pick delta this. But that's not right because delta cannot depend on x, right? Delta can depend on epsilon, but not on x. So let me write it here. So not okay. Yeah, that's too light. Not okay to pick delta equals epsilon over x plus 2. Delta cannot depend on x. This is important because a lot of people did it last semester when trying to do limits. You somehow found it easy to, you know, just do this and say, oh, let's pick this delta, and it's not right. So what we need to do then is control this quantity over here, right? Make it so that it's not that big. And we can do that because well, because x is we can choose the delta, right? So if we make the delta small, then this cannot be. So what would be the problem? Let me put it that way. Let me put it a different way. See, the problem would be if this number becomes very tiny. Because if this number becomes very tiny, epsilon over a tiny number becomes huge, right? So I don't want this number to become tiny. So I want this number x to be away from -2. If x is close to -2, then I'm in trouble, right? And how can I guarantee x to be away from -2? Well, because I can make x to be close to 2 as much as I want, right? So then here's where you pick a number that would make it work, right? The only thing I need is to be away from -2. So I'm gonna go and just pick distance 1 from 2, right? So here's how the rest of the argument usually goes. So assume delta is less than or equal 1. If you assume that, then if 0 less than x minus 2 is less than delta, but delta is at most 1, that means x minus 2 is less than or equal to 1, strictly less, actually. So this is what I mean. And what this means that -1 is less than x minus 2 is less than 1, or when I add 2, 3 less than x, I mean not 3, 1 less than 3, right? And this achieves what I want, right? Now my x is kind of far away from -2, right? X is between 1 and 3, and that's good. It's far away from -2. It's all I wanted. So then I can see if I can control x plus 2. So then what happens with x plus 2? So then x plus 2 is between 5 and 3, correct? And more importantly, 1 over x plus 2 don't need the absolute value bars because it's positive. That's the other thing. So 1 over absolute value of x plus 2 is the same as 1 over x plus 2 because it's positive, right? It's greater than 3. And 1 over x plus 2 is, what is it that I want? Greater than, less than. I want, I think I want greater than. Well, I mean, I can have both of them, right? Let's see what we have. We have 1 over x plus 2 is less than 1/3, and 1 over x plus 2 is bigger than 1/5, right? Whichever one of those two I'm gonna need. All right, I think we're ready. So let me show you why I think we're ready. So let's go back to what we had over here. So we wanted to make delta this number, but that doesn't work. Now instead we can use 1/5, I believe, right? Because if we make delta epsilon over 5, then okay, so I'll write it down and I'll explain what I mean by this. So we assume that delta is less than 1. That's fine. We can make it whatever we want. And then, so let delta be the minimum of 1, and I think it's going to be epsilon over 5. All right. Good. Now, because delta is less than 1, then 1 over x plus 2 in absolute value is greater than 1/5. That's the work we did before. All right. Then also, if 0 less than x minus 2 less than delta, well, because delta is less than epsilon over 5, we have this, right? So then x squared minus 4, which is x minus 2 times x plus 2, well, this will be less than x minus 2 will be less than delta, and x plus 2 is less than 5. But 5 delta is less than or equal epsilon. And we're done. All right. So we use this number x plus 2 to control. So the fact that we let delta be less than or equal to 1 allowed us to bound this part with 5. That's where we're using this 1. So we use this 1 so that we could bound this other part. For the rest, we simply use delta, and delta is less than epsilon over 5. So maybe I write it over here, epsilon over 5 times 5, which is epsilon. All right. Questions? Yeah, so Ashot, I see that you asked if we should have used the 1/3 or not. And here's the thing though, when you do it backwards, when you take a look at here. So in here, if you make this less than epsilon over 3, you cannot go back because you want the inequality to go the other way. See, that's the problem with working backwards. When you work backwards, you need to make sure that the arrows that go the other way are the ones that work, right? which is the problem when we start with what we want and try to figure out how we can start. See, the problem of doing that is that you need to realize that the inequalities you want are sometimes reversed. Okay, so this is one way of doing it. Now, like I said, this one was arbitrary. We could have picked any other number here, 1/2 to almost every other number. You cannot get as far as, what is it, 4. If you pick 4, that would be too big, because then your number can become close to 0, and 0, x plus 2 equals 0 would be a bad thing. But as long as you pick anything smaller than 4, this argument can work. All right. Moving along. So this is now the criterion that I was telling you about, where we're going to tie this concept of limits of regular functions with limits of sequences. So this is going to be the sequential criterion for functional limits. So instead of writing it down, actually, what I'm going to do is I'm going to show it to you on the book. So, and we'll do the proof. So here's the result. So it's an equivalency of limits. It says, given a function, as we had usually from set A to the real numbers, and a limit point, the following are equivalent. The limit equals L, or for all sequences in A, which with numbers that are not equal to C. None of the sequences have numbers equal to C, but they approach C. It follows that f of xn approaches L, right? So observe what we're doing here. We're relating the limit of a function with limits of sequences. So a short way of saying what this theorem says is the limit of a function is L if all sequences that converge to C, when you apply the function, they converge to L. And I said all sequences, but I really mean all sequences where the numbers are not equal to C. So again, the limit of a function when you approach C is L if every sequence that approaches C has a property that when you apply the function, the sequence approaches L. All right. So let's prove this statement. Proof. And we're gonna first assume that the limit when x approaches C is L. So we're gonna go and do the limit, the proof with the arrow pointing in the positive direction. All right. So this part. So let's start with this. Okay. So what is it that we need to do? We need to consider a sequence. So consider a sequence xn inside A such that xn is not equal to C and the limit of xn is C. So we pick a sequence that approaches C. And now I need to show that when I apply the function, the f of xn, so I'll write it here, need to show that the limit of f of xn is L. All right, and then as usual, how do we show that a limit is L? Well, we pick an epsilon, right? The limit of a sequence, right? We pick an epsilon, and we need to show that for numbers big enough, the difference between these two is as small as we want, right? Okay. But I gotta use my assumption. I gotta use this at some point, right? Okay, so let's pick an epsilon. Let epsilon be greater than 0. And I need to show that this and L are closer than epsilon, right? Okay, so how do we do this? Well, let's use my definition, right? What does my definition say? My definition says that for this epsilon, so since the limit when x approaches c is L, then there is delta greater than 0, such that 0 less than x minus c less than delta implies f of x minus L is less than epsilon. And let's label this star. Okay, good. Now I also have to use the property that my sequence, the limit of my sequence is C, right? What is this definition that the limit of my sequence is C? Well, the definition is that for a number, whatever number you pick, there's gonna be an capital N, such that if the little n is bigger than the capital N, then this number and C are closer than whatever you told me, right? And I want to combine that with this one. See, this one already has the conclusion that I want, right? This already has the conclusion that I want. So I want to use that I have the previous part. So I'm going to pick delta. So because limit of xn equals c, using delta, we know that there is some capital N such that what? Well, such that xn minus c is less than delta if...
Professor.
Yes.
We cannot see it.
Yes. Oh, thank you. All right, so let's do it again. So I want to use this limit, the limit of the xn equals c, and I'm going to use this limit using delta in place of epsilon. And what I know is that there's going to be a capital N such that xn minus c will be less than delta if little n is bigger than capital N. All right? Okay, and we're set now because look, this part, so let me call this 2. This part is exactly what I need to put in here, right? So now, if little n is bigger than capital N, then this is what happens. First, xn minus c is less than delta by this part. And then by start, by this one over here, f of xn minus L is less than epsilon. So what's the conclusion? The conclusion is that the sequence f of xn, I can make it as close as I want to L by picking n sufficiently large. So therefore, the limit of f of xn is L. And that proves half of my proof, right? We showed that, so let's backtrack. So this is what we showed. We showed that if the limit is L, then for any sequence, and you pick a sequence that approaches C, then the limit of that sequence is L. Now we have to do the other one. The other one says if all sequences that are of numbers that are different than L, different than C, approach the functions approach L, then the limit is L, right? So conversely, let's do the other part. Now we're gonna assume that for every sequence xn with xn not equal to c and xn approaching c, we have that f of xn approaches L. So let's suppose that happens, that every sequence that approaches C, the value of a function takes it to L. And we need to show that the limit is L, right? So we're gonna do it by contradiction. Let's suppose that the limit is not equal to L. By contradiction, suppose that the limit of f of xn is not L. What is the meaning of that? Of limit not, yes, this limit not being equal to L. So we need to do the negation of this statement. So the negation of this statement is that for every epsilon, so the limit is for every epsilon, there is a capital N such that these two are closer than each other. What is the negation? The negation is that there is an epsilon. There is some epsilon 0 greater than 0, such that for every capital N, there is some little n bigger than capital N, such that f of x n minus L is bigger than epsilon 0, right? That's the negation of the limit definition of a sequence. It means that there is some epsilon such that the numbers that are in the natural numbers, the difference of these two is greater than or equal epsilon. Okay. How is that going to be a contradiction? Well, it's almost you can almost see it here, right? I mean, if we have this on the one hand, we get this. This is a sequence that will not be convergent to L, right? It's away epsilon 0 from L. So all we need to do is specify what is the sequence that we want. So here's what we do. Since this works for every capital N in the natural numbers, so we simply call xn the one that corresponds to the corresponding capital N. So in this way, we created a sequence xn all right, so we're just missing something. Okay, so let's see, where is it? Yeah, so the only part that we're missing here is why is this sequence approaching C? Mm-hmm. All right, let me backtrack a little bit because I'm okay. The contradiction we should have used here is So, okay, so the thing we want to contradict is that the limit of f of x is not equal to L when x approaches C. So this is, all right, so let me correct this part over here. It's easy, but not as easy as what I was writing. Okay, so let's try this again. So we want to show that the limit of a function is L when x approaches C. What is the contradiction of that? The contradiction of that is that there is some epsilon greater than 0 such that the limit definition does not happen. So what is the meaning of the limit definition doesn't happen? Well, it means that there is an epsilon greater than 0 such that for all delta, there is x such that 0 is less than x minus c less than delta, but f of x minus L is greater than or equal epsilon. All right. Okay, but something was not right, but now it's correct. Yes, so this is the contradiction of the limit definition. So the limit definition is for every epsilon, there is a delta, so that this happens implies that happens. The contradiction is there is some epsilon such that for every delta, you can have the first thing and the second thing doesn't happen. All right, so all we need to do now is pick the appropriate delta. So because this works for every delta, we can pick as my delta the sequence 1 over n. So let delta be 1 over n for every n in the natural numbers. So then what do we get? Then we get xn such that, so I'm calling it xn, the one that goes with delta equals 1 over n, such that this happens and f of xn minus L is bigger than epsilon. All right. Okay, and we're almost done here because look, this happens means that xn approaches C, right? Because no matter what, you can make 1 over n as small as you want. So this, we can make it less than epsilon. So the limit xn is C, and xn is not equal to C. Right? Xn is not equal to C because of this greater than on this side. And this shows over here that the limit of fxn is not equal to L. Is not equal to L. Why? Because it's always farther away than epsilon, right? Than epsilon 0. All of these numbers, f of xn, are farther, are epsilon away, epsilon 0 away from L. Therefore, this limit cannot be equal to L. And this is a contradiction to this part over here, our assumption that all the sequences had to go to L, which is a contradiction. All right, so this is a very strong theorem because it will allow us, this theorem will allow us to use all the other results we had for sequences, right? We had two important theorems, you may remember. One of them, we call it the algebraic limit theorem, and the other one was the order limit theorem. And we can now use those two together with this one to establish properties of limits. So for example, let's take a look in our book, and it will be a direct implication. So this one over here, We corollary 4.2.4 is called now the algebraic limit theorem for functional limits. And this is what it says. It says you have two functions, f and g. The limit of the f when x approaches c is L. The limit of the g when x approaches c is M. Then the following properties happen. We can take constants out of the limit. That's property 1. If you do the limit of a sum, is the sum of the limits. That's property 2. If you do the limit of a product, is the product of the limits. If you do the quotient of two functions, it will be the quotient of the limits, provided you don't divide by 0. Why are all these true? Well, very, very straightforward. This is how you would prove any of these. Say, pick for example 2. Well, you say this, you start from the left-hand side, the limit of a sum, right? So you know that by the previous theorem, the limit of a sum is going to be whatever if the same happens for every sequences, for every sequence of points that approaches C, for every sequence xn that approaches C. And but we already know it for sequences, right? We did it for sequences. That's the algebraic limit theorem for sequences, that this property holds if we do it for sequences. All right, I guess I can write maybe okay. So let me. I'll show you the details for 1. For example, number 1. So number 1 is the limit of k f of x when x approaches c is KL. All right. Let's try to argue why this one is true. All right. So what is the property we know? So we know that that property holds for sequences. So we know that the limit of KAN when n goes to infinity equals k times the limit of an when a goes to infinity. This is the algebraic limit theorem. So we proved this before. So for regular sequences, we can do this, right? So then what? So, well, then now you pick a sequence. So let xn be a sequence. Xn approaches C and xn not equal to C. All right. So what is, and suppose that, so if the limit of f of xn is L, sorry, if the limit of f of x when x approaches C is L, which is the property that we have, then by our previous equivalency, our sequential equivalency, then we know that the limit of f of xn is f of L. Sorry, L, not f of L, L, for any sequence, right? So then, what would be the limit of k f of xn, fxn? Well, by the property that we know this for sequences, we can take the k out. So this is true, and this is true for all sequences. And because this is true for all sequences, then again, by our previous theorem, that the equivalency of sequences and regular limits, then we know that it's true in general. and this is K times L. All right. Okay. So I'm gonna stop right here. Yeah, somebody is asking me already that to save the recording. Yes, I am saving this entire session. I know that for some of you, your internet connection became bad. I don't know if on my end or on your side, but this is not gonna we're gonna have this video of the entire session available to you guys. All right.